Okay, so let's try to connect these things. Anyway, it's hard, and I just want to, I mean, that's a fun thing, but it is hard to make. I mean, we have these fractal generators for landscapes and so on, but that was kind of an impressive adjustment. In terms of like actual research, it's hard to make a landscape that then you can erode in a room like this and get real kind of network structures out. So people have gotten somewhere with that, but that's a hard thing to do. Okay, so I'm going to try and connect these. I know I'm taking a long time, but I'm going to connect these scaling laws. This is just to sort of start this section off. This is a paper that appeared, as you can see, 2014, just a few years ago, that tackled this. We have this, as I said, this problem. We don't have the history of the evolution of a landscape, right? Because we just don't have a way of. We don't have satellite data from 10,000 years ago, because we're just too stupid to have invented it by then, or whatever, right? So it's hard to see how these things have changed. But you can get in there and say, I think you can. This is okay. So piracy on the high keys, right? This is a terrible pun of mine, but piracy is a word that people use in geomorphology, talking about these things. I mean, look at these. This is to try and make it more exciting for themselves, because it really isn't. But there's an aggressor and a victim. I mean, this is just unbelievable nomenclature. Anyway, but the idea is, there's a divide here and there's stuff going this way, and it's going to eat into this divide. It's going to be steeper on this side, and there's going to be more erosion, and this is going to balance itself out. Right, so and we talked about it a lot with hot models and lots of other things in POX, right? So they're sort of, there's a really fundamental story to a lot of systems is equilibrium, right? And that's been a big thing. But then there can be equilibria in dynamic systems that are about other pieces. And for, say, the hot model, it was creating structures that minimized risk, or in the sense that they're distributed evenly. And so this is a dynamically evolving landscape. But there's something going on that is going to move it towards a kind of an equilibrium type structure. There's no risk or anything. It's more of a simple kind of traditional physical system, I suppose. Anyway, this is an effort to sort of see the history of things and actually kind of try and tease out some sort of evolution. But this is the basic idea, right? So you do the sort of thing that we described at the start of this lecture, which is to find out where all the networks are, and of course you have these slopes and so on, right? So you can start to think about how strong the erosion might be, right? If it's really shallow, then you expect erosion to not be as strong. There are some, this is all a bit of madness. There are some odd heuristic things that people have come up with. It's very rough, but basin area is roughly correlated with slope, and if it's not balanced properly, then you can sort of assert that things get out of control. That's what this funny little measure is here. You don't have to worry about these too much. Okay, so there was some other pieces in here. Will it? Oh, okay. This is just 2 minutes. All right. Yep.
To most of us, river networks appear to be fixed features of the landscape. In fact, many rivers define political boundaries that have been in place for centuries. But what if those boundaries are moving? Scientists have long suspected that river networks are not as static as they appear. Some rivers look distorted, and others contain rocks or aquatic organisms that can only have come from other rivers that aren't currently attached. This suggests that rivers have been shifting and moving across the landscape over millions of years, but until now, there has been no way to measure this change. Researchers at MIT and the Swiss Federal Institute of Technology have developed a mapping technique that measures how much a river network is changing and in what direction it may be moving. The technique focuses on a river network's drainage divides, the ridgelines that separate two neighboring river basins. As rainwater flows down either side of the drainage divide and into opposing rivers, it erodes the underlying rock, creating an imbalance in the river network. To reach a balance, the drainage divide must shift to assume a more stable pattern. With this new measuring technique, researchers can determine the direction in which a divide would have to move to bring its river networks into balance. Knowing where river systems are shifting may help scientists understand how these rivers shifted, diverged, and merged over millions of years. This knowledge may help solve some long-standing mysteries in geology and biology, such as why some rocks and fish that seem to belong in one river basin are also found in another.
So that was, that's a little press release type thing, just for a couple of minutes from MIT. But this was really impressive. No one had been able to do anything quite like this, and seems to have some good legs to it. We have to include in here. I know we discussed it in our reading group in complex systems. Just reminds me of this, of things being in the wrong places. But salmon in trees, for example, right? So this is that forest network story, right? The trees are all connected and communicating with each other. It's kind of a spectacular, beautiful story, right? But there are trees with salmon bits inside them because they've been absorbing stuff from, they're not just next to the river. That's the thing. This stuff being communicated through fungal highways, which is incredible. I mean, it's a beautiful, beautiful, incredible complex systems Tolkien-like story of the trees are alive. Okay, I'll write that down for myself. Fish trees, that should be enough. Okay, so, that's a whole world of things, but you can see lots of fun with these little, there's probably MATLAB involved in that one. You can see with the excellent color scheme choice, which should be, I think, is outlawed now, right? Well, it's not the default, perhaps, jet. Yeah. Anyway, so lots of fun making little landscapes evolve and so on, but it is a pretty big story. Of course, geologists think this is all just nonsense because it's just like the little crusty bits. All the big interesting stuff is happening on the inside, and you've got these geomorphologists who are doing very insignificant work. But we live on this stuff, so it kind of matters, right? We worry about it exploding, and anyway. You'll love the discipline thinking. Okay, right. So I'm going to talk about this, and I'll definitely get through it this week. We have, let's get my stick out. Yeah. So network architecture, right? We have Horton's laws, and that seems to, just the way it's laid out, it has 3 parameters, and there's a 4th one, but we've sort of said that you can figure out that these things are the same. But it has one for area, one for length, and one for number. These ratios, these Horton ratios. So it seems to have, it has 4 parameters. Tokunaga has only 2, but Tokunaga really seems to tell you what the architecture is, right? So what's going on with this extra stuff? There's a simple redundancy, which you guys will figure out. It's a little, very difficult calculation. But the main stream length and stream segment length ratios are the same, at least theoretically. And so we could start with Tokunaga's law because it tells us how things fit together, and then try to march up through, try to produce Horton's laws, right? So this is well known, actually, right? So Tokunaga figured this out in, I think, 68. After proposing this way of thinking about the architecture of networks with side branching. So we'll go through that to start with. So there's one piece, and this matters for blood networks obviously as well, and it's an interesting story there. So space filling, and so you could, right, so with these networks will fill space. You can imagine, of course, across a continent you have different kinds of structures, you have deserts and so on, so the networks become more sparse and so on. So that's a little bit of a funny piece. But certainly for blood networks, you want to get the energy to the whole system, obviously, right? So there are some debates about whether the capillary density, I mean, there shouldn't be debates, but there have been different observations, and it's a little bit messy, as to whether capillary density increases or decreases, likely decreases as you go up through mass, right? So elephants may have capillaries a little further apart, maybe. Although when you take a mammal cell out, like how can you tell that's from a a gerbil or from an elephant? It's an interesting question. Mitochondria matters there. But yeah, we need these things to fill space. All right, so for river networks, we'll talk about drainage density, and that's going to be the inverse of the typical distance between channels. And this is, using an old term, but that's reasonable. It's like how, right? So really finely, you can have really finely sort of fine branching networks fitting into a system, or they could be wide and far apart, of course, right? So this is going to vary across different landscapes. So for what we have so far, you can, so it's an inverse, you can calculate basically you add up all the lengths, right? So you go along here with a little meter, you measure all the lengths of these things, add them all together, and they're going to be stream segments. So we're going to add this one, and this one, this one, this one. If we wanted, so area divided by stream segment length would give you a length, right? And it would be a typical distance, if you like, between between adjacent pieces, right? So there's a typical distance between these two streams, and then there's a divide in here, which isn't shown, but there's a typical distance between them, which is a similar quantity, and then we'll take the inverse of that. All right, so this is a density measure. So this is just something we kind of have to have floating around. It's characteristic of a system. Okay. And so you start to do a lot of these simple little things, these little pieces, right? So we're going to sum across over the basin. We have a number of stream segments. That's this n sub omega. That's what we've defined. They have a typical length. So we add all of those up and divide by the area of the whole basin. That's the piece. So lots of little sums like this. Okay, so if we start with the Tokunaga law, let's see if we can figure this out. And we're trying to get to Horton's law for stream orders, for the numbers of streams of certain orders. So there are less, right, as you go up through stream orders, right? There's only one of the dominant order in the basin, and there are many little ones. So this is written in a way such that this is greater than 1. So we can do this in rough ways, and then you can do it in more and more clever ways. So we want the number of streams of order omega in terms of other stream numbers. Right? So this is we'll have to think about how we do this. So let's get a picture. All right. Okay. Okay. So just because of the way we've laid out how stream ordering works, okay, so here we have a stream of order 4 starting, and that's been generated by these two order 3 ones hitting it. Right? So if an order 3 runs into another order 3, we get an order 4, right? So for every order 4 in this basin, we're going to see 2 of these. Yeah? So we don't have to know Tokunaga's law for that. It's just a stream ordering piece. And also for every order 4, that's where we get Tokunaga's, these side branching things, right? Okay, so first of all, there's going to be, for every order omega plus 1, there's going to be two times as many order omegas that are creating them. Think of them as creating them. And then for every order that's above, so here it's 3, for every order above 3, so 4, 5, 6, 7, we're going to have this Tokunaga ratio telling us how many of these side branches there are, right? So order 3s can appear in this network as ones that combine to make an order 4, or they could be side branches for order 4, 5, 6, 7. Okay. So we have these two ways of adding things up. So there's a set of these, right? So this is going to be for orders. And so if we still have order omega, it's going to be for order omega plus 1, plus 2, omega plus 2, and so on, right, as we go up. And there'll be more of them, right? So this number is increasing as we move up to higher and higher orders, right? Because there are going to be more side streams. Seem all right? Right? So we have the thing is we have a rule for this one. We're going to take Tokunaga's law and we're going to have a rule for this guy and then try to figure out a relationship for the others. Okay, so putting things together is going to look like this. So the number of streams of order omega, every time we see one of those omega plus 1 streams, that means 2 of these have created it, so we put a 2 there. And then we have to sum from the order above up to the order of the basin, and that's where we put our little Tokunaga ratio piece in there. So this has to be true, okay? And so it's using this finer story. All right. So we can put Tokunaga's law in there, so it's going to be just all that matters is the difference. This is going to be replaced by T1 and then RT to this power, to this blob as a power minus 1. So you put that in and play around with this little calculation. You have to think about it a little bit. It's an interesting thing. And you'll get this piece out, which is cool. Very cool. And Tokunaga figured this out. Actually figured out and thought I was like, wow, this is a cool thing, but then realized that Tokunaga had done it. Okay, so there is a solution to a quadratic, but you want that positive thing, and you can think about that as well. All right, so that's nice. That's a nice little piece. Okay, so so that's the stream number, and we can connect this to the stream length ratio, right? So again, we'll assume we have side streams. We assume that they're roughly separated by this density, 1 over the density. So we have a typical length scale that tells us how finely chopped up this landscape is by this network, how it's incised. So we want to use Tokunaga's laws, it's exciting, to estimate the length of this stream here. Right, so this will be an S3, typical size of an order 3 here. Well, the way to think about this is we need to count up all of the side streams. So if we count up all of the side streams for this, so we're going to ignore, so it's made here, and then the side streams for here, there are order 1s and order 2s. So we know how many order 2s there are and how many order 1s there are, and then we sort of think that roughly these guys have a typical distance between them. Sometimes they'll hit close to each other, but there's some typical distance between them. So if we count up all of them, and then add 1, because that's a small correction, but we add 1 because there's another gap at the end here, multiply it by the typical distance between them, and that'll give us an estimate of that length. And there are lots of other fine-grained things you can do with that, but this is the basic idea. So if this is order 7, then we need to know about we need to use Tokunaga's law here for order 6, 5, 4, 3, 2, 1. And that'll give us in total the number of side streams, add 1, multiply by the typical distance between them, and then you can calculate away. So we're just going to stick this straight in. If you look at as we increase omega, and this is really just a geometric sum, all that's going to happen is, and so you can calculate this, all that's going to happen is this is going to end up just growing as Tokunaga's ratio to the power of omega, right? Because the dominant piece will be that next term that you add. And so as a result, this thing is growing as Tokunaga's ratio to the omega. So this is, the stream length ratio or the mainstream length ratio has to match up with this. So this is a much simpler story. So that's kind of a nice thing. So the two pieces fit together. That's what this is. So we have mainstream length, stream segment length, their ratios matching up with Tokunaga's ratio, and then we have this piece. So now, right, so here's Horton's stream number ratio, mainstream length ratio, stream segment ratio, and the connection to Tokunaga. So that's this is a good thing to see. So exciting. All right. It is, but like I said, it's a little bit odd, right? We start with 4 parameters for Horton. We saw that there were really 3, or you'll figure that out. There were 3. We've still only got 2 for Tokunaga. And there's also that, so there's the area one as well. So let's see if we can do something with that. Okay. This is invertible. You can certainly invert this, right? So we could get, obviously, straight away we have RT as this guy. We could invert this as well to find Tokunaga's ratio in terms, sorry, T1, this parameter, in terms of Rn and RL if we wanted. So, you know, you should be able to derive it's possible you could derive Tokunaga's law from Horton's laws. Okay, so these depend on, so these Horton ratios depend on these pieces. That it's pretty clear that the Horton ratio for area will as well. There's some redundancy, and in fact, it's true that this is, at least theoretically, this is true. So that's a nice thing. So actually, the Horton ratio for number is the same as the Horton ratio for area, and that's a really nice observation. So, and then you can go crazy and start to say, well, these are really laws of statistical things and averages, but we could worry about the distance between these guys, and they have exponential distributions, and then start to try and fit, really think about this architecture. So there's a long, and I won't show you all that. I'll just touch on that. But we went a long way into that, and I feel like if this was all done again, we'd come up with a better version for stream ordering. When I say we, I mean many, many people. Okay. All right, so this is the inversion that I talked about. So once you've got these parameters, you can find T1, you can find this, but there's no Horton's ratio for area is not there, so because we can get we must be able to get everything from the Tokunaga's law. It seems like there must be some, redundancy over here. Those three parameters should become 2, and as I said, it's as simple as the number ratio being the area ratio. Okay, yeah. And so this is an argument, and this is not an obvious thing, but this sort of after the fact, we can go back and sort of, maybe argue for why Horton's laws actually should give you Tokunaga's story. I mean, after all, Tokunaga did intuit this, right? So let's say we start with this little stream structure here, and we magnify it by the stream segment ratio, right? So it's grown up by this factor. Then we know, at least if we sort of, this is a renormalization thing, if we then sort of looked and could see the full scale, then, and this landscape was, properly drained, then we'd have to see these side branches in here. And they'd have to appear in a typical way that goes against that stream ratio number there. And that's the story there, right? So you scale up by a factor of RL, that means we're going to have to add omega minus 1 streams in here to kind of, we're going to have to add a whole set of omega minus 1 streams in here to kind of, to sort of have this thing draining in the same way, and the ratio will have to be, the number that we'll add will have to be, again, this Horton number. You don't have to worry about it too much, but you can kind of go back the other way and see that's reasonable. Right, yeah. Okay, so I'm not going to worry about that too much. Yeah. Yeah, that's okay. Yeah. Okay. All right, so area number. Okay, so these are the stream ordering statistics I showed you for these 3 big networks. There's mainstream length and stream segment length here, right? And so those two scale in the same way, something we've talked about a bit. This is stream number, it's decreasing, and area is increasing faster. And it makes sense that it's increasing faster. Area grows, obviously, roughly as the square of length. So this is growing at a faster rate. And so this is true in all of these. If you then take the number one and flip it upside down, right? So we're going to take this plot here and flip it, and we'll do that again, and we'll do that again. You can see that they're growing in the same way. So this is pretty suggestive that the ratio for numbers and areas, for number and area are the same, right? All right. So let's see if we can figure that out. It's a nice little problem. Okay, I have a little piece in the middle. This is the horror of of scaling stuff, and I mean there's some. Let me just show you a little piece here. This is fun. So this happened just the other day. Twitter Clauset. Aaron Clauset, who we've talked about. I don't think he tweets too much, so we should be able to. Yeah. So here's the first post, right? It's not threaded very well, but it's excited to share this new work, right? So scale-free networks are rare, from Clauset and another character. So they go through and they look at lots of, I haven't looked at the paper that well, but they're getting data sets out, and right? So super weak scale-free, weakest scale-free, weak. I guess there's weakest and then super weak. So they're really trying to put some hurt. There's strong and weak, so there's sort of nothing like in between there. You need the ambivalent. Anyway, so words matter, people. What's that?
I just wonder if they originally had weakest, and they're oh shit.
We need a absolutely, truly, terribly weak. So he tweets this. This is from a bit over a week ago. So let's see if this threads properly. Yeah, so what if this is a byproduct from it, right? Sample networks, because a lot of small networks, if you look for a parallel, it's not going to work out, right? The thing is not big enough. So there's some going fast. So Ferrara's over at USC. Ryan Gallagher worked with him. Let's see. Yeah, there we go. Soleil comes out and says, this is an interesting exercise of so-called data science. It's been 18 years of work. And I sort of bring this up as a modern version of that Mandelbrot-Simon argument stuff that I showed you in Parks, which was very amusing. And then he's alerted Vespignani and Barabazi. He's said, look at this. And then, so there is definitely an issue with, of course, you get lots of small networks that the people have said are scale-free and they aren't, right? Fair enough. Let's see, where do we get to? The reply must be down here. Well, they're going, I don't think it's there, actually. Okay, but it is, he retweeted them. So, right, so here's Vespignani. He's not happy about it. I thought we were past this since more than 10 years, da-da-da-da. So they have a big argument. Oh boy. So I thought we were too. Anyway, so this.
Arguments used to be relegated just to the journals, and now
Now we're gonna have
which is great actually, because now
Sure. No, it's good.
see it and not have to subscribe to science or nature.
They should, yeah. Peter Home, he's got a blog post full of confessions about power laws, he's coughed up his thing. Vespignani said, you probably haven't looked at the right, you're looking at small ones. He doesn't tweet so much, so he must be in here. Look, they're all arguing about it here. So right? Not happy. We've never changed our definition of small network, blah, blah, blah. This is Duncan has a go at him here. He goes, you really think the original claim had been real networks exhibit something other than Poisson degree distributions? Anyone would have been interested. It's really shifting the goalposts. He's not happy. Anyway, so, oh boy. So some people got a little, just step away from that. Anyway, that is to say, this is a long time ago, and people have worried about this for a long time, and it's, we've kind of been there. But this is sort of early efforts to sort of contend with the horror of this. I mean, this is the range of orders, right? So this is just sort of running a little thing where you vary the range, the start and stop, you just vary them over all possible things. And then, right, you're just fitting, it's just a linear fit. So here are all these important parameters, right? So the Horton ones for number, area, length, and stream segment length, and then the ratio of those two. And this is to sort of indicate that actually, regardless of where you take that range, you get pretty good agreement, right? The between these two. It's always the measured area ratio is always a little bit greater than the number one, but this is to sort of show you that it's fairly robust, even if there isn't a pure, like a perfect scaling sort of thing. And these things don't vary too much, right? I mean, this is a standard deviation, and this is this is sort of a primitive analysis, I suppose. Obviously, if you're going to do, this is just 2 data points, right? So this is a ridiculous thing to regress on, and it's to show you how it breaks at the end, which is fair enough. But, it's something people have worried about for a long time. So, you can slide your little window around and get lots of different, it can move in nasty ways. Even though your linear regression thing says, here's the slope plus or minus 0.001, right? It's like super confident, but, similar sorts of things here. This is the Amazon again. It's that column on the right shows you that, it does seem to be that these ratios are pretty close. So here's a rough way of trying to calculate that. Anyway, people are still, classic, that's a paper that's just a week old too. So they're still like trying to stick the boots in. I don't know. Yeah, there are heavy tail distributions of all kinds, and they really matter. So, okay, so let's see. So we could do this, and so I know this is a new thing, so maybe it's a. You have to concentrate with this. There's no super, we're not using crazy math to do anything. It's sums and so on. But just thinking about the architecture of these things, let's see about this piece, right? So here's the area of a basin of order omega. It's going to be the number of streams of order omega times the average length of them divided by this divide thing, because that gives us then, what that's giving us is a typical kind of sleeve around this thing, right? So it's true actually that while this is draining into this point, there's all these little side pieces draining in here. So, and that's true here as well. So the area that drains into this stream segment is everything that's in all of these basins that are connecting it, plus all this little side piece here. So you imagine all these little sleeves that we're putting around it. Okay, so what happens is, so this is an estimate of area. Let's do these different things. So that's going to be, this is the number of streams of order omega. There's only one, right? There's one at the largest scale. And then as we move back in order, we get this factor more, right? So there's going to be, if this is 4, there are going to be 4 of the order below, and then 16, and so on. And the difference is how that grows, right? So we start with capital omega, subtracting down until we eventually get to 1. You could do this in different ways, but we definitely know there's 1 at the top, right? We know there's one big one. So it's useful to orient it like this. So that's the sneaky thing. We do the opposite for stream segment length, where we have a typical length scale for the smallest one. This is just something we know about our landscape. And then we increase up from that. So that's that's a sort of a carefully chosen way of representing these quantities in terms of their Horton ratios. Again, start with there's only one of the main one, and so on. So there is a slight problem with this, and it turns out not to really matter. But to do the calculation really properly, you have to use Tokunaga's law, because this is assuming a really hierarchical structure. There's this one stream, and then there are 4 of the next down, and then 16, and then 64. But it's not quite true. And the reason is, here's a slightly difficult thing about these architectures, right? So there are all these second order ones that are going into 3, and there are, second order ones here, right? So these second order ones are going into this 3. But there are second order streams that are going into 4, 5, 6, and not contained all those basins. Right? So we're doing all the ones not necessarily in order to basins, right? Because all the ones that are hitting here, they're not fitting in a simple way. Yeah? So we're basically saying for every order 3 stream, there are, let's say, 4 order 2s. But the calculation that we did before, where we connected Tokunaga Tokunaga's law properly to stream number. You know, there's going to be a stream of order 4 out here that's going to have 2s hitting it, and 5s out here that have 2s hitting it. So you have to be very careful about how this thing fits together. But this is a rough thing to do, and it will work, basically, is the story. Because let's pull out constants, right? So this Rn to this omega, we can pull that out. We can pull this quantity out as well. There's an R sub s, I'm just going to take out, that's at -1. We'll pull that one out here. And that will leave us with a nice little object here, which will be an R sub s to the omega on top, and an R sub n minus omega, and we'll put that on the bottom. We're sort of going to assert that this is less than 1, right? I mean, we're a little careful with that, but I'll just sort of say that right now. This is typically sort of 2 and 4, so these, in terms of the way things fill space and so on, it's okay. We have to be careful about that. This is repeating what we had on the previous piece, just a geometric sum. Omega is 1 to capital omega. Is that actually? Oh, yeah. Yep. So I've pulled out a factor of Rs over Rn. That's this piece. And then this is an omega minus 1, and then the sum is really from 0 to capital omega minus 1, and that's the right thing there. Right. I guess it's okay because there are separate fractions, but this is a little bit upsetting. All right. See if I remember that. Okay. Oh, we've really ran out of time. You kind people, you really, okay. But there's our upshot, right? We get to this. I'm very sorry about that. Talking too much. Looking at Twitter. Wow, so bad. Okay, all right. So we'll pack up and go. But if you want to come over and talk, I'll be there until 11. All right. Thank you, people. Sorry. Okay. Good. Okay. All right. All right, we talked about the cat. What else? Okay.
Lightheart actually won like a sort of math communication.
Yeah. Okay.
This year.
Really good. Yeah. Awesome. Yeah. So she's still doing. Maybe she's at some sort of professional level of that now, right? Like that's what she does. I have to look that up.
Doing stuff with virtual reality.
Oh. Okay. There we go. We're gonna do it. Robots. Sorry. Anyway, always a good source of things. Okay, so let's see. So we had all these. So I was trying to connect all these Horton laws together with Tokunaga's laws, right? So this is a structural story, and then we're going to sort of zoom out from that pretty quickly. But the last piece we got to, and I guess it was all in a bit of a rush, was this little calculation. Again, just quickly, there's a lot of these sort of things you can start to piece together. The area of this basin, or if it's in us, right, it would be a volume that a blood network is servicing. And then, of course, it would be a volume here. But this, you'd have this same sort of structure. You'd have a typical kind of cross-sectional area of a vessel, if it's in 3D. Here, it's the typical kind of width around to the drainage divides around a stream segment. So that's really just a constant for the landscape. So we're going to add up all the stream segment lengths in here, multiply by the number of them. And this is a rough thing, and as I was trying to say at the end of last lecture, is that it's fine, it works out, but it is doing something a little wrong when it comes to how these things are structured. So a big deal about natural. And again, we don't really have a theory for this, I don't think, but observationally at least, and I'm going to use these two examples over and over again, river networks and blood networks. There was this side branching structure that was identified by Tokunaga, right? So this kind of mixed hierarchical structure to these distributional supply networks. It's not something we would emulate. If we make networks, we tend to sort of just build a big pipe and then break it up and then break it up and break it up. It'd be interesting to look at, I guess that's interesting. I wonder what we've done with some of our plumbing systems and so on in cities, yeah. Maybe it's true. Okay, so this idea of a pure, this seems to be sort of a pure hierarchical thing, right? So that's how that calculation seems to work. But the truth is that, say these are second order ones, there are second orders that will not end in a third order. They will end in fourth orders and fifth orders and sixth orders. So it's going to be, there are second orders that are outside of third order basins, which is just an important thing to understand. But this calculation works roughly. It's just one of these simple little, it's a geometric sum. You just have to do the right, you just have to be tidy and neat with these things and so on. But the end result was we were trying to find how the area of these basins, and capital omega is always the overall basin's order, that we showed that is going to be growing as the number ratio, right? This is the number of streams, how they, it's actually how they grow as you go down in order, right? So this is greater than 1, typically around 4. So this is all a constant here. This is, as omega becomes large, it never becomes very, very large, as we sort of talked about. 12, 13 are big numbers here, just like a order, it's logarithmic, right? A magnitude 12 earthquake would be, the earth goes pop, I think, right? Yeah, I think so, like an egg, yeah. That's not going to happen with a gooey caramel center. Yes, okay, so this is a nice thing, right? So this is sort of observed in different ways, but we kind of put it together that Horton's laws collapse into these two pieces, right? So there's really just a ratio that we'll need for the number. It works for area as well, and then a ratio for how these lengths grow. And as I've said, I'm sure we could do a better job than this. It sort of took me years, because you get buried into this thing, and this is the way everyone's done it, and you're like, oh yes, this is all very smart and good, and it is good, but I still feel like we could do a better job. Okay. Right, as I said, it's just a rough argument. You have to do the side branching thing properly, and that's actually an assignment question. It's a nice thing to do. Yeah, this is a nice thing. So this is unpublished. And I'll try to explain why it's not published, apart from just not laziness, just no, fear and uncertainty and doubt, FUD, always good. The combined area of basins of a certain order, right? So we could take all the second order basins, and they've got, there are this interstitial space between them, right? They don't fill up all of the space here. And same with the third orders and fourth orders as we zoom out and zoom out and zoom out, and even the first orders, right? They take up some space, but there's all this space in here that isn't a first order basin. So we could add all of those up, and if it was a strict hierarchy, then that area would just get bigger, right? So the first orders would comprise all of these little pockets. Let me get this silliness off. I shouldn't say that. Tower is a beautiful thing. Okay, so right, okay, you're dead. Someone secretly leaves all of the bad ones. Okay, must be how it works, right? So these are little first order ones. So if it was all sort of, they look like eyeballs. So you can imagine, if it was hierarchical, you'd add up all of these, and then sort of this would be the combined area, the total area. And we'd have omega here, and 1, 2, 3. You can imagine that this just goes up, right? Because we're, if this is a sort of a pure hierarchy. Right, because these ones, they don't do everything, but there are twos around them, and then there are sort of, and so on, right? So these twos would be a bit bigger, yeah? And eventually there's this order omega 1, which would be the size of the whole thing. So it would go up. But it's not really how this works, right? So there's a basin of order 3, and I know I'm drawing this ridiculously, but then, so this is we've got another 3 here, and this is a 4. There's a basin of order 2 here. So there are 2s outside of the 3s. And right, this is an odd thing. This is because of the side branching, right? Okay, so the question is, this is not right, because of side branching. Right, mixed hierarchy. or which is the same as this sort of mixed hierarchy. So there's this kind of nice result, and it's a bit more powerful than it can't really matter about the stream ordering, right? So, and so here's the observation straight up from this result that we had just now. So if you have the number, the ratio for number and the ratio for area, so as we're going up through orders, the average size of an order 1, 2, 3, 4, 5, it grows, and typically it's around 4, and of course the number of them diminishes by that same ratio. Right, so the areas are getting bigger, but you're getting a factor less of them. And those factors are the same. So the number of basins of a certain order times their area, average area again, is roughly constant. So this actually goes like this. I'll put this. Seems to go like this. And so that's an interesting thing. So this is, I mean, it's to do with the how do networks partition space, and it's kind of an odd thing. This is our result. Okay. So let me see, I've got a couple of graphs. So you see it's not perfect, and it has to deviate towards the end, which makes sense. Because eventually, this whole basin is contained like this. And it's going to be a bit wrong for the first order ones because, of course, we're down there at the grid scale, and it's a little messy. But pretty constant through here, slight growing. Pretty constant through here, it starts to grow, and because there's only one of these, and there's maybe 3 of these, and so on. And pretty constant across there. So, and they're all about 60%. And again, this can't matter entirely in the end about ordering, right? So it could be if we just take all the basins of the same size, then it should roughly have a story here as well. Okay. So this is sort of sitting around. I call this equi-partitioning of landscapes, that somehow there's this nice way, the way the landscapes are divided up, so you get this kind of equalization of basin. Yeah, total basin drainage. And so it's weird. It's well below 1, of course. It's down here around 60%. So the question is, I think this would be something we could publish if we could kind of estimate what that is. And I don't know why I haven't done that. Okay. All right. I think that's interesting. Okay. So this is a neural reboot situation. The one I wanted to show you, and I don't think it reloaded. This is so we can just feel better about ourselves. It's just this. Come on, little guy. I'm really not going to apologize for this. The sound is really important, so let's see if we can get that. I don't know why sound is so hard to get to work on this. Can you hear any sound? No? This is important. Let's spend 15 minutes getting the sound to work. This is really vital. Such a strange thing. I mean, you'd think it would just be a nice knob that says sound. Let's try over here. Seriously worth it. And then we'll go into something else, right? So sound, it goes out to the Creston. Come on. DisplayPort. Such a shame. Maybe I can get it to... One more. Roundness. Okay, so that's always good, you know? You want to break between things. You could go to the fridge and eat food, or you could watch someone else do it. And this is Round Animals, apparently, is a Twitter feed, because there are Twitter feeds for everything, right? So, oh my God, it's just so great. Nature is Amazing is the title. He go. Someone's done a really good job with the Steadicam on that one. That's good.
There's a version of that where they like make the hedgehog all blue, give it like little red shoes.
So when the hedgehogs rise up, that will be like, yeah. Sonic? Oh, yeah, I see. Very good. Sonic, thank you very much. Sonic the Hedgehog. Oh, I'm clicking on that thing. Okay. All right. I try to give you these little mental salves, right, so we can... Really is weird about the sound, though. I don't know, like with the special things. Okay, all right, okay. So, hierarchical self-similar structures. Hierarchy is mixed. Tokunaga's law is this sort of beautiful thing underneath it. And we've got connections between them, and I'll give you a few problems so you can play around with these things. Anyway, yeah, and they're just like little sums and so on. You just be careful with them and kind of set them up right and so on. There's no, advanced measure theory or something ridiculous. It's counting stuff up. Yep. Combinatorics people, it's like just very easy. Okay, and then this took a while to get here, right? But we have this story now that there are only really 2 Horton laws that they fit together in this nice way, and we had that Equi partitioning thing, which I feel like is a bigger story that we just haven't quite told the world about. Okay, so I mean, it's true that sometimes it takes like at least 10 years to write a paper. It's just like it has to go fallow in your idiot head, and then eventually you figure it out. And it's good that it takes some papers infinity because you should not write them. So, but it is a weird experience, to live long enough for that to happen. And the crucial thing about life is to date everything as a result. Presume you will be around and put a lot of things like this, right? 2018-01-25 thing. Really good later on. Really good. Okay. We could have a whole lecture about that. Okay, so only 2 parameters independent. So we end up with this kind of nice story that we just had this really clean thing from Tokunaga. This seemed to have 3 and originally even 4 parameters, but actually we got it back to 2, and we can go back and forth between them, even though this seems to imply and people sort of make mistakes about things because it looks like a pure hierarchy. The goodness is all in here. All right. So let's go back out to sort of so there's another way to attack this, and I've mentioned this, which is we'll just get rid of the stream ordering thing for a while. It's very helpful to try and understand how things fit together. But we could just pick a random point, and then we'll ask, what's it, so some random point. It could be on the network, and I think that's the way it's structured. It could be just a point in space, but we'll ignore those. But so random point here. Of course, one thing that we've ignored in all of this is width, right? And maybe depth as well, but there are also other pieces. Obviously rivers get wider and deeper, and blood networks, they're thicker next to and that's a big piece we'll get to later, I suppose, but really just for blood networks. So we pick a random point, and then we look at the basin. So let's say it's this one, and there's some basin, right? We find the basin that drains into that point. What's its area, and what's the longest stream in there? And then, of course, you have things like the characteristic Euclidean shape of the thing, right? Length and width. So we can talk about now kind of a probability distribution because we're randomly sampling from this network. What's the probability that it has a area A and an area length? So this is /E double L, which Dave Dewhurst is your he's the sort of assistant deliberator for this course. If I haven't mentioned that yet, I realize I should have. And he will be both your TA and grader and all those sorts of things. He's going to help out with office hours. He told me the other day that he's made every L that appears in any math thing that he writes in LaTeX look like this, which is well done. Anyway, so it's a nice L. This is what you get. You get a power law, and it's A to the minus tau and L to the minus gamma. We're using notations for those indices, for those exponents that you often see in the literature. Of course, people go and measure things from different places, and you see this is roughly the case, that the exponent, so this is a fatter tail, right? It's a smaller exponent, and we, of course, always write these in a way that, so we have A to the minus. This is a positive quantity, right? This is always a good way. Whenever you have any understanding that something will be positive or negative in here, you absolutely must indicate that. Anyway, so these numbers are, these are smaller than these numbers, which means on a log-log plot, the area distribution is going to have a shallower slope than the length one, which makes sense, right? Area is length squared, so bigger things. But we'd like all these things to, so how does this fit together with the stream ordering thing, and how do these things fit together with each other? We've talked about these things in Pucks a little bit. Okay, so we've talked a lot about these power law distributions, or at least heavy-tail distributions for probability distributions or frequency distributions for sizes, right? So, and they matter a lot. And so we sort of frame this as the statistics of surprise, right? So the normal distribution, yes?
For the drainage basin containing P, which drainage basin are you talking about?
Yeah, so you take, so you can rescope this, right? So we could, this could be one that's for a whole continent, or we could take a, you know, a particular basin and so on. And then, so it's going to keep working within. Yep. You know, and of course you don't go down to too small a point. But that's, that whole self-similar structure is, yeah. So you want a large enough one for which you've got enough samples and so on, yeah. And there's always this problem of, you know, the slopes are hard to measure and it's messy and all these sorts of things, but it's, you get these tails, it's pretty good. So something we haven't talked about, and I need to put this in somewhere properly, is these slopes can be hard to measure and these distributions can be hard to measure, but a very powerful thing is to look at these things at different scales, right? So we might take this basin and find its power law size distribution and then find a bigger basin and so on. And you'll see how and you put them on the same plot, you see how the larger scale cuts off, right? And then you can do some work which is called finite size scaling. So it's a big part of complex systems, right? I mean, lots of systems are made out of different, lots of little parts, and they have different sizes, whatever it is. I mean, for people, you know, we can think of our wealth as one aspect, or your number of followers on Twitter, which is apparently an important thing, et cetera, right? And how many of those are bots? But, you know, you have different sizes for things. You know, for biology, you've got just the number of organisms of certain species, and they all have to fit together, and so on, right? Okay, growth mechanisms are very important usually in how these things get this way, and of course, you know, there's a clear growth thing that's happening with these networks. Optimization is at work as well, and we had that nice example from the MIT thing about piracy and so on. So there's you know, definitely a movement towards equilibrium of some sort. All right, so we want to get to the mechanism, and as I've said, it's not really there. There are lots of little growing models and so on, but I don't think there's a universal one. Okay, so we have this detailed picture of branching networks from Tokunaga, really. We'd like to derive these things, and so we're just going to set this up, right, for a couple of, for just the probability of length. See if we can go from this sort of detailed structure to this big story one. You know, and when you're getting out to these probabilities, you're just sort of randomly throwing darts at this thing, and you're not thinking about how things are connected together, right? So if you just have, if someone just gives you this distribution and a distribution for area, and then says, you know, make a network out of that, that's not going to be super easy, right? In fact, probably the easiest thing would be to make a pure hierarchy. All right, anyway, okay, so we're going to imagine that Horton's law is just what we sort of did for the area calculation, that they hold perfectly, right? Okay. And then we just do something like this, and we bite the stick, right? Okay, so and just sit down and sort of work through a calculation. So I'll give you the outline of that. It's nice to do these things. As we did in Pucks, complementary cumulative distributions are always good things. Cumulative distributions appear everywhere in statistics, but often with these power law type ones, we want to look at the complementary one, which I'll use this kind of notation. So it's the probability that when you sample whatever it is, in this case length, that it's greater than some quantity, and we'll write that as length star. So that will be the probability length is greater than, so this is this notation. Here the little greater than, and so it's going to be whatever we have, a sum or an integral depending on our distribution, in this case up to L max. And for these distributions where we sort of think of them as going off to infinity, you know, we allow this to go to infinity, right? Okay, so complementary cumulative, it's going to be 1 minus the cumulative distribution. You'll see the words exceedance probability. We've talked about these things from some familiarity. I remember these things. But the big deal for power law type distributions, and you know, exponentials work as well in a useful way, is when you integrate a power law distribution, the exponent pops up by 1, right? So if we have a -4 power law, which is a pretty weird one, then we'd have a -3 for its complementary cumulative distribution. Integrating is smoothing, right? Differentiating is smashing things up a little bit. So integrating is smoothing. So we always get better things to look at, and statistics work better on them. So this has been a game that people have been happy to play for a long time. But as we showed the other day, people are still tweeting some shade at each other and writing papers of shade. Should have just thrown out that GIF, the one that has the shade coming across the buildings, that one. That's high quality. Like the little cloud that goes and just says shade. I said GIF, right? Yeah. Okay. I come from a time of GIFs. Okay, so, all right. So this is the calculation, and I'm just putting it in here. We've done this a bazillion times. Out of the minus gamma is the character we're interested in. We do our integral. It's just the simplest little bit of integration that you can do. Right, so the exponent pops up by 1. We're framing this as minus a positive quantity. It's going to be minus a positive quantity again, so we keep our little minus sign out here because we're good people. This is, right, it's going to be small, right, out at L max, and so the minus sign here, we're going to have 0 minus this blob evaluated L star, so that cleans that guy up. So it's going to be proportional, as I said, to this L star quantity to minus, and the exponent will have decreased by 1. All right, so that's a good way to work with these kind of distributions for measurements, but it's also analytically useful. So we're okay with this? Remember this little thing? Yeah. All right. Turn page. You can tell me to turn page. This is my oldest daughter when she was really little, right? So you're reading books and they have no idea what a book is, right? They just don't know, what are we doing? And but I remember like realizing like we're going to work on the mechanics of reading a book, which is, you know, I mean, it depends on your language, right? But we're going to turn the page, and that's a big deal. So that was the first instruction. We would say things and read they were apparently eventually understood to be correlated with the words on the page, but the turn page part was a big deal, which I got her to do. And now she reads tweets. Or Tumblr. Wow, so great. Should never teach people to read. Okay, so, no, she's an incredibly smart person. So, yeah, it's just great moments for me. Okay, so let's see. So we're going to do this thing. So we're going to try to figure this out using our stream ordering. But we're not, because of stream ordering, it's pretty coarse, right? So we sort of know about these points like somewhere along this stream, we could be along this stream. We kind of, you know, we have an idea of how everything works from a stream ordering point of view, so we can roughly do this. All right, so we're going to have some spatial resolution, this capital delta, and we're going to have a nice grid. So we'll kind of cut things up like that, which is also true of our data, so that's useful. And the idea will be we'll approximate this complementary cumulative distribution for length as the number of squares that we find that have, right? So we're going to have a grid on top of this, and then we're going to go to each grid point, and if it has a mainstream length, if we have a basin there that has a mainstream length greater than this L star, then we count it, and if it doesn't, we don't, and then we divide by the total number of boxes. Fine. Right? Okay, it's a bit of an odd thing to do, but this is fine. So we have Horton's ratios, Horton's laws, and we have in particular the one for stream segment lengths, right, which will tell us roughly how long this one is, and roughly how long this one is, and roughly how long this one is, and of course we know the number of them. Another Horton law. Okay, so we're going to say, let's just anchor our, I really don't have my stick. I must. Let me find a stick. Such an important thing to be doing right now. Oh yes, here it is. I was going to use a pump. I could use a pump. No? I'll use a pump for a little bit. Okay, good. It's a very nice pump. So this is going to be, we're going to say we know about these guys, right? Because our little stream ordering thing works at these scales. So let's just say, let's start at some omega and take that length. Right, so we're just going to insert it in there, and this is the sort of crucial thing, right? So we're assuming Horton's laws work in this pure hierarchical sense. We've got a basin that goes up to some order, capital omega, this is 10 or whatever it is. This is going to be the total stream length, length of streams in the whole network, right? So what we're doing is, estimating it, because these are averages. We're going to add up, we've got all these streams of length 1, order 1. So we count all of those, and we multiply them by the average length, and we count all of the 2s, and we multiply them by their average length, and so on, so on, so on. And then we're just going to divide by this length scale, and that'll give us the number of boxes, roughly, right? So we're sort of fitting this little kind of a fractal story. It's going to give us roughly the number of boxes that we required to cover this whole network. And there are boxes in here that have nothing inside them, right? No network inside them. So we've done the right thing. And then we want to find then we want to count the number of boxes that cover parts of the network, where if we stand on that part of the network, then there's a basin that has a stream that has a mainstream length, right? If we travel up there, that's greater than this thing we're interested in. And the way that's going to work is, we just start this sum, so everything looks the same as this one, but we'll just start the sum at omega plus 1, right? So we're very sure that, not very sure, statistically at least, every point on let's say this is 3, an order 3 thing, then every point on an order 4, 5, 6, 7, 8 stream segment will have a longer mainstream length, right? It's in a bigger basin. It's in a basin of a higher order. What has happened?
Is this kind of like a generalized box counting?
Yeah, it's like box counting. Yeah. Yep. And we're fitting these little boxes. I mean, we're doing it at a bit of a, we just well, look, there's a grid behind it. So imagine this is a very fine grid. Yep. And then as we sort of make that grid finer and finer, we're going to have a bunch of little boxes that fit on this one.
But it's still like a probability because it's like just how many boxes they divide by.
Yeah. So that kind of, so imagine, so you exactly have that view, right, of the number of boxes required to cover it. That's some scale. And of course, as we move that scales in an interesting way, right? That's the fractal story. But now we're going to do two things with it. We're going to have all the boxes required at some scale to cover it, and then we'll light up those boxes that cover the ones that are, right, exactly. So you can imagine like 2 of these pictures, and then you have all the boxes here, and then only the boxes that are covering, say, in this one, this one.
This is assuming that the streams have no width.
Yeah, or that we're not going down to such a small scale that it's, Yeah. Yes, it is a crass and terrible thing to do, but it will work. So these are going to cancel out, right? Drink. Using the excellent package cancel, also canceling. And if you add up all of this stuff, right, as we showed before, this is basically the area of the whole thing, because we've added up all of the stream segment length, and if we multiply by a sort of a characteristic width of these things, then we've got the area of the whole basin. So that's really what's happened here. It's the area of the whole basin multiplied by the drainage density. Yeah. So, which is the inverse of this characteristic width. So total area divided by the characteristic width of around a stream would give you the length of all the streams added up. So this is just overall constant. You know, and we're not making our boxes so small that it's not true, and they're not so grossly large that it's not true either. Okay, so using Horton's laws, or let's get this right. So really it's just the top piece, and we really just have this sum. The interesting thing now is that it's going to start at omega plus 1. It's going to go to this fixed capital omega, and then we just have to be a little thoughtful about how we do that again. It's again best to start with the fact that there is one stream of order capital omega, so then we can count backwards from that. Do the right thing. Yep. Yeah, right. So when this omega prime is capital omega, this is just 1. This is to the power of 0. So that's going to increase correctly as we go backwards. And we have some characteristic scale for the length of these first orders, and we can build up from there with the Horton's law for stream segment lengths. And really, these are the only things that matter. There's a little r sub omega here, and then this little character here. The rest are constants we can pull out. Yes. Well, not quite true. We have to be careful with this sum. So we always like having sums that start from 1 or 0 and go up to something. So that's what we're going to have to do, right? We're going to flip this upside down. Yes? You guys will work through this for area, so this will be a good point. So this is just what we had on the previous slide, so if you're still looking at that, that's okay. So as I said, we can throw a few things away. And this is really the interesting piece that's doing the scaling. And then the usual little business, we have to sit there and concentrate and worry about 1s and 0s and starting at the right bit. Yeah. But if we start with omega double prime, we're going to say that let that equal to omega minus omega prime. Then we're going to have a sum that'll start in a nice way and will go in this direction, and that'll be a better thing. All right, so I've got the things written down. So, okay, so when omega prime is capital omega, right, this sum goes from small omega, normal omega plus 1 to capital omega. So now we have 4 omegas. That's great. A capital 1, a basic 1 with a prime, one with a double prime. I'm very sorry. So, but when this omega prime is capital omega, this is a 0. So we're going to have a 0 there. And when it's omega plus 1, we're going to put that in here. We're going to have capital omega minus little omega minus 1. And that's what's on this next line. So now we have a new sum. It's going to go from 0 up to here, which is fine. We like zeros to things. And we'll have to replace this piece here with our new character, which is, right, this is going to be, we have simply omega prime equals omega minus omega prime, and we'll just flip them around. So omega prime is omega minus this one, right? So we're going to take this, second line, and we're going to put this blob. That's where we write on the board, and we make a terrible mistake. We're going to put it here. This will be capital omega minus omega double prime. I wasn't at this, so someone was telling me years ago, there's I guess it was back in the day of having like overhead projectors and stuff, and this Russian guy had come through, and it's sort of a complicated, messy thing, but he's sort of out of his head a little bit, and he's doing the slides, and he sees there's a mistake, and he just goes at the board with the thing, and it's just projected onto a wall, and they're just like, and everyone in the audience apparently just went, no! The most drama you can imagine in a. Anyway, just sort of attacks it. Yeah, it's tempting. You get confused. Like I guess I could be trying to do this. That would be, God. Okay. Problems with magic rectangles. Okay. All right. So we're just fiddling around with things. We're just taking our time and making sure we, end up with something that looks like something we knew before. Right. That's how humans operate a lot. That's right. Yeah. we shortcut it a lot. It's like, that is what, I know this already, which is a terrible mistake usually. But this is, we're getting it back to just a plain old geometric sum. So, but doink. This is what all of that does with our new omega double prime thing. So this is fine. It's a blob to some power, and it goes from 0 to a blob. So that's good. It's a geometric sum. We can also get rid of, again, this is now a constant that we're not worried about, so we could throw that out. It's really just the omega double prime, and we're going to flip this upside down because it's always good to have a positive power. And we know, generally speaking, this is sort of 4/2, so we have a sense that this is greater than 1. That's important. So it's growing. This is a growing sum. So it's going to be dominated by the upper term. And whatever this is 0 to something. So the sum is going to be dominated by the something to plus 1. So capital omega minus 1 plus 1 gives us that power. Okay, so that's a lot of messing around, flipping around with things. Again, we've got a capital omega. We don't really worry about that. The dominant piece in here is going to be just these ratios to this. This is our variable, right? Right. We're interested in what's the probability that it's greater than a particular length. We've been able to at least connect a typical length of the order omega streams to order omega. This is not quite finished, right? Because we need to express this in terms of L omega. So there's one last little sneaky thing to do. This is the geometric sum story here. Okay, so there's no out of control math, but it's just like being careful with things. Yeah. Obviously you make horrible mistakes and then you clean it all up and pretend that never happened. Yeah. Because math. Okay. All right, so just think about this for a second. We have to somehow we need to get this back in there. And what we know is, let me write it here. These things. We know that L omega is scaling as RL, right, to the omega. This is the Horton's law. It's growing in that way, right? The typical size, and good, which is RS omega, right? So this is the stream segments. This is the length of the basin, the mainstream length in the basin. Words. Okay. So what do we want to do? So this is how they're connected. So we've got a blob to some power over there. So there's different ways to think about this. You could just say, let's take omega out of this, right? Take logs, right? So we could have ln of r omega like this. This is, of course, some constant. So we'd have to be a little bit careful about that. Plus, and this is like behaves like this. Plus omega ln of RL to the omega, and I'll put S's. Boop, boop, boop. Okay, so we could do that. And then we have an omega, and we could play around with it. Just stick it in. All right, well, let's try it. We'll do it in a slightly different way. So not a bad way to do this is to... So there are different ways to smudge this around to get the right thing. So we could take whatever... This is blob to a minus omega. That's... we can always write that as... whatever blob, we can always write a blob as e to the log of that blob. So that's what this is. Yes. And this is our story here. We need to express the right-hand side in terms of this typical scale here. Yeah. And so we know this is how it's growing. It's growing from some typical length for the first order streams. And so we can do the same little game here. This is sort of avoiding taking those logs back there. It's proportional to this, so it's e to the omega ln of r and s. So it's almost like this. Okay, and I'm sorry, I have to jump onto another page. Okay, so what we're going to do, okay, so we have L of omega is equal to this blob. Okay, so we just need to kind of make that thing exist. So let's do that. This is what we've gotten from our calculation, and we're simply going to put an L omega in there and divide by ln of Rs over here, right? So that ln of Rs over here, this guy divides by this, it gets back to E omega, and then we're just back to this structure here. Yeah? But we've noted that this thing is our L omega. So now we have L omega to some power. And if we play around with this a little bit, this is ln of Rn divided by Rs, so that's ln of Rn minus ln of Rs, right? Log behavior. So that's what this is. So a couple of things will cancel. This one's going to cancel here and here. So we're going to end up with the typical length scale for an order omega basin for the mainstream length. It's going to be to that raised to the power of minus this ratio of logs plus 1. This is a complementary cumulative distribution, right? That's what we were aiming for. So in fact, we've identified it very nicely, right? So this piece here is gamma. Okay. So I know this was just some like working through some math, but it's kind of nice that it all ties together, and you can see now that this is odd, right? We don't even for simple random network models, we don't really have values for these guys. But we know that they actually will connect. I mean, we don't have analytic values, we can estimate them. Log of, in this case, the number, and then log of the number ratio and the length ratio are involved. Okay, so I'm sure you're thrilled about this, right? So you can do this. You can do a similar thing with the area calculation. So probability of area, decay is a to the minus tau. And you play around with all of that. And eventually, actually, you see it's 2 minus 1 over gamma. So they're connected to each other, which is nice. So you see this is the scaling relation story where we have different scaling laws, but they are connected. So this took, decades for people of measuring these things separately to start to see that actually they kind of looked, or they, if you look across basins, there was sort of a similarity to them, and toy models have this connection as well, even if they have nothing really to do with real networks. So scaling relations, very nice. And then we'll do one last one, which is Hack's law, and we can do this pretty quickly. So this is this length to power is proportional to area to the h. We can use Horton's laws again, so this won't take as long. This is how length grows, and this is how area grows, and we're going to identify it as, we're going to put the number ratio in there straight away. So you can just do this sort of thing. Length is growing as same kind of manipulation. Instead of just rs to the omega, we're going to make it e to the log, right? And then we'll create an area piece in here. We want this. This is e to the log n of Rn, so this is really just Rn to the omega, so this is going to be our area piece. And to make that, we would need to divide through by ln of Rn, right? So that would get rid of this piece, and we'd be back to here. So we're just sort of building it out because we think they're connected to each other. Right, and then this collapses back, as I said, to Rn to the omega. This is some blob. This is, of course, the scaling of area to the omega. So that's our story. This is the average stream length is growing like this with area. There's some scaling here, scaling exponent, and that's going to be this Hack's law exponent. So we can do this one page. Right. So again, it's that same ratio appearing again. So that leads us to, how am I doing? That leads us to starting to see that a lot of these things are collapsing, can be derived from the same thing. And in fact, this is a good plot. All right, so if you go through, and so we went through with at some cost for you, psychologically, we worked through this one here. We worked through this one here just now, right? And I told you what this one does, and his Hack's law as well. So the story is that all these laws here, they have all these exponents that can be connected to each other, right? So there's this kind of weak fractal scaling for the mainstream length That just sort of sits by itself. This is usually just a bit greater than 1, if anything. It's pretty weak. And then we have Tokunaga's law here, 2 parameters. We can, if we want, connect them to the Horton parameters. And then here are Horton's laws, and then here are these bigger ones which don't have stream ordering built into them, but Hack's exponent, for example, we've just derived, it's connected to the Horton ratios, and then we'll just say H is, we'll just use H after that. And so as you see down here, it's just the fractal exponent D and Hack's exponent. So those things are just appearing over and over again. So all of these are tied together. So if you have one of these, you can derive the others. And this is a really great thing to be able to do with a system, right? Is to say, okay, we've made all these observations. Many people have kind of attacked it in different ways and shown these kind of nice scalings and things. And eventually you come through at the end and you say, well, actually there are really only 2 parameters that describe this. This is a long effort, really, 60, 70 years, of course, and that's spanning the time that we figure out the satellite thing and start taking pictures and digitizing and build the web and all that sort of stuff, build the internet. It sort of spans have computers, spans an interesting time in history of science. But as I said, we don't really, I feel, have, we have all these connections and they're all, it's all mathematical, it's all derived, right? We can say this, but we don't have a mechanism that everyone thinks is fine that says, oh, H is whatever. Okay. Speaking of evolution, right? So computers and screens have gotten better, so this has become 8-bitified or whatever. So here's a really simple model that has lots of nice things in it. It's a fun thing to play around with. Random walks are great things, right? I like random walks, and I know I talked about them in POX, but the world likes them too. They appear in all sorts of ways. Randomness is a really big feature of everything. So here's a really simple little network model, right? So you can start to think, oh, I want to erode a landscape, and I showed you this sort of elaborate one that Bruce Shaw and Marcelo Magnasco had made, and then lost. The only remains were a VHS cassette. It's pretty slim. So here's a ridiculously simple one, and you can think of sort of stuff falling down like paint on water on a glass or something, but it's more about sort of just a slope where there's some sort of erosion going on. And so it's a triangular lattice, because that's a great lattice, and at each point on the lattice you just flip a coin and say that the flow is going to go this way or this way. That's all, right? Very simple thing to do. So that's what this is indicating. And what's very nice about this is there's lots of random walk stuff in here. The first return problem is in here actually, which is a thing we highlighted in POX. If you remember that, right, what's the probability that if you have flipping a coin, what's the probability if you start off at 0 that the number of heads minus the number of tails gets back to 0, right? So, half the time you're back there in two flips, right? Flip a head, flip a tail, or flip a tail, flip a head. But actually, on average, we had that very odd result that you expect an infinite amount of time to pass before you get back to 0, which is really awful for gamblers. They kind of deserve it. It's okay. Sorry, that was moralistic of me. Anyway, it's good for the people who make money out of them. So, good. Wow, these are tough terms. So, but the probability that returns after L steps, and it has to be an even number, decays as L to the minus 3 halves, which is a really, really heavy tail, Okay, so those things appear in here because what we have, and I'll show you this, is if you think about the drainage divide, right? So don't think about the streams. Let's start here and think about how big is this basin that starts here. Well, it's really the divides are actually random walks themselves. So you have 2 random walks going up here. And eventually those random walks will go, right? With probably one, we expect them to run into each other. But so you'll have these random walk boundaries, and so when they hit each other, That's the end of that little basin. So the typical length of a basin actually has exactly this probability distribution for the first return thing. It's that the probability that, pick an arbitrary point, the probability that it's a basin of length L, because here there's no fractal scaling, right? It's just the longitudinal length and the length of the basin of the actual stream will be the same up to some factor of whatever it is. And that will decay as L to the minus 3 halves. And so the area will be in there as well. So all right, so let's do these calculations, right? So the boundaries of random walks, as I just tried to explain, for the basins and their first return problems. This is then connects into all sorts of nice mathematical problems. It's actually, you can think of this as this is a hard thing to work with, but you can think of it as a partition of, and this is say, an area of a certain sort. We'd be interested in, how many basins are there of a certain length, because then we sort of turned it this way, and also of a certain area, right? What's the joint probability distribution? So that's a difficult thing to work with, but it's interesting. And it's a kind of, partitions are very famous for, in pure math. This is something where it's an increasing partition. It's not just ordered in that way, right? We'd have to think about partitions of integers where it's ordered. They have to increase. So it's another kind of partition problem. Because we've got this random walk, right? It can't go back this way, right? We're thinking about time going this way. So that's just a little thing on the side. Might be fun for some people to think about. As I said, right? We've got these guys, and this is what pops out of all of that. Right, so this is actually the derived thing after n time steps, and n has to be even. This is the probability that your little random walker returns, right? It's sort of, it's going away, I suppose, but the framing was always that this is your drunk friend, right? Which is sort of like, it's not great. Just confused, right? They're confused. You let them go, and they take random steps away from where you are, and you're worried about them coming back. You should be very worried, because on average it will take them an infinite amount of time. So they should pack snacks. Okay, so L to the minus 3 halves. So we also expect, in a very sort of naive way, right, the typical excursion of a random walk, if we've got time here, it grows as t to the half, very famously, right? So the normal distribution for the location of that random walker, the standard deviation grows as t to the half. So we're going to expect that. We're going to have a length of n, and we're going to have a sort of a typical excursion of n to the half. So we're just going to multiply those things together. So the area is growing like length to the 3 halves, and length will be growing like area to the 2/3. So we have this very nice model where this is Hack's exponent, right? It's greater than a half, which is what you expect from dimensional analysis, right? Length is meters, and area is meters squared, say. And so you find all of these things. You get this is the exponent for the area, probability of area. The area, you select a basin, it has an area of A, in fact, in case is A to the minus tau. It's a 4/3, which is 2 minus 2/3, right? These all fit together, these scaling relations. Gamma is 1 over h, right? All these things are here. Tau is 2 minus h, gamma is 1 over h, they all fit together. There's no fractal scaling, so d equals 1. So this is a universality class where we could say these two things. We might want to say d equals 1 and h equals 2/3, right? That defines this network. So if we went out and found one in the real world and just measured some things, we'd probably look at it and think it looks pretty random anyway, but this is the sort of story where we'd say, oh, it really is in this box. And one thing we've always been very interested in with systems is, are there these sort of discrete set of universality classes, right? There's this kind of network, and then maybe there are some other kinds, and there isn't sort of a continuum in between them, or maybe there is. And as I said, the Horton ratios are harder to define. Equi-partitioning, again, this thing that's just sitting around. See, this is a subtle point. I'm just going to throw it in here, right? So we've gotten to these power law size distributions. And I just want to go back and mention this because this is part of it. So now we've got a to the minus tau. So think of this as counting, right? This is a number thing, we're counting. So if we multiply area times the probability, then this story suggests that we should get a constant, right? Because the number of basins of a particular area times their area seems to be roughly constant. But that's actually not true, right? When we look at the power law thing, because this is a to the minus tau plus 1. And this is usually around, well, say for, for Scheidegger, for example, this is 4/3. So this is actually a to the minus a third. It's usually greater than 3/2. Smaller than 3/2, yeah. So what's going on here? Like, why is this decaying? And it's because when you look at it in this way, you're overcounting things, because there are basins within basins, right? Because now you're also thinking about, it's more of a continuum story, and all of these, there's this basin, and then this basin, and then this basin, right? So if we, in this little dx in here, you've got all these basins, as we sort of go along here, that all have the same area, basically, right? They're all being counted. So they're not, so what you have to do is kind of say, well, this is not these are not separate basins, right? We're partitioning this landscape, but when you do this calculation, you're actually counting all these basins that contain each other. So you get this, so things don't work. You don't see it from this point of view. You don't see this equi-partitioning, all right? Because you have to enforce this thing. Say, I really don't want to count this one, but because you're now sort of looking at a continuum thing, you tend to count too many. Okay, that's where that should have been. Right. Okay. I will talk about this, I think, just really briefly the next thing, but let me just say this, right? Horton's laws, Tokunaga's laws, these are all about averages. And so you realize, these things have all this variation. What happens when we do that? And so that's a real problem, right? So here's just a little bit of it. This is, say, this is actual real data, right? This is Mississippi. These are underlying length distributions for order 3, 4, 5, and 6 basins. Here they've been rescaled, right? We're rescaling them, and there are just some useful choices you can make here, and put on a logs, put on a different. Actually, it's the same thing. There's really just log here, yeah, and then this is just a normal scale, a linear scale. And so you can see, it's a bit harder here, but there's this kind of peak, this peak, this peak, and another peak here. They all fit onto some sort of universal distribution. So, what we've been doing so far is just saying, this is the length of an order 3, this is the length of an order 4, this is the length of order 5. All of those calculations have just been about having these, like a Dirac delta distribution, right? There is just one length. It all fits together perfectly. But actually, there's this big spread. So this is a bit problematic, right? So we have to sort of think, well, does this all work? This is what we call a scaling collapse, where you have these different distributions, and you know how how to rescale them. It's really quite a nice thing. You can do some nice pieces. So you can say, we have all this internal stuff, right? So say we have an 11th order basin, like the Mississippi. But we know all about the 3s and 4s and 5s. We have lots and lots of examples of those. We have good statistics for them. So in this case, we've taken the order 3 ones and the order 4 ones and rescaled them. And then this is a plot of this. What this shows you is this is the actual overall length of the order 11 one. So you could scale all the internal ones up to the largest scale. You only have one sample of the largest basin, right? There's just one of them. And there are 3 or 4 at the next order, order down, and then maybe 16. This is the average for that. So the point is, like, this is just one way to say, this whole basin is internal. It's consistent with its internal structure. So it's not so bad, and you can play around with these things, and you'll see, for example, the Nile. This is how much longer the overall one is. This is in 10 to the 3. The ratio is here. So this is what you would expect estimated from the internal one. This is the actual value. So the Nile, and we know it, right? The Nile is it's a long basin, right? So the point of this is to show that, the overall structure is not the same. This is sort of a nice little calculation to make. Very quickly, I'll just show you that there's madness, right? You can start to do all sorts of things. It turns out that there are exponential distributions for the gaps between these things. We assume that to be all constant. You can play around with that. You can get here are these exponential distributions. You can start to convolve them together to make those internal distributions. Then you have to convolve these together, and this is the power law on the outside. So it's convolutions of convolutions and so on. So you can actually really go deeply into this architecture and see at this sort of micro scale is like just randomness of how things fit together, and then start to kind of put it all together, and you'll end up with a power law size distribution at the outside. So that's a lot of pain and suffering, but I just want to show you that it's kind of there. Generalized Tokunaga's law, I'm not going to talk about this, but you can generalize that in ridiculous ways, statistically, right? This sort of thing. Okay. Yeah, you don't need to know. This is bananas. Okay. Look at this, just madness. Unbelievable. Unbelievable. And they're weird distributions, right? They're not like normal distributions or something. This is this weird particular distribution. We end up with this kind of underlying thing. Oh my God, wow. Okay, this is just to sort of show you that it can go into madness, and I'm not going to put you into that. But all of this was to try and understand how the architecture of these networks. I think we really absolutely have that now, but it still remains to come up with sort of a beautiful story, or find the beautiful story or ugly story. It doesn't have to be beautiful. Truth is not beautiful. For how these networks grow, but we'll have more about optimality of networks coming up that I feel pretty good about. So we'll get to that, right? So your insides, it doesn't matter if you're a pig or a human, right? We had those examples. There's kind of a broad optimality of getting stuff from one place to the other. Talking too long. That's what I do. Sorry, I will stop that. Got a question? No. Everyone can run away, of course, because you are liberated. Okay, so I was going to do the last section of this branching network stuff. Let me do that, and then we'll have some pieces in between, and we're going to get onto optimal supply networks. How do we structure things to make them spectacular? Okay, let's open the right object. This one. Okay, so as I said, this is sort of a smallish piece. Where do these networks come from? Are they going to be, we'll get to a big story actually about river networks and blood networks, but this is there's width to these things, but this is sort of this one-dimensional, locally one-dimensional structure that's branching and forking again here. This is filling a 2D space, this is filling a 3D space, so that ambient dimension will matter. This is, we're 3D things living in 3 dimensions. This is a 2-dimensional surface living in 3 dimensions, so that will matter, which is an interesting piece. Okay, so let's just talk about a couple of things that have been floating around. This was sort of, geomorphologists had thought this was the kind of explained everything, and someone came across a beta lattice or a Cayley tree and just said, okay, that's going to be our little toy model. And so these are quite charming things, right? It's from the 1800s, I think, originally, yeah. And the idea is you just make an infinite graph that has locally the same degree, right? Everyone has the same degree. So this is a degree 3 beta lattice, but it's rooted at a point as well. And this was sort of used to talk about, say, nuclear explosions and so on, right? How things take off. And of course for contagion and so on, this is sort of the basic diagram, right? So of course we think branching trees apply to a lot of things, and they do. But the problem with this sort of thing, which is a great fun little mathematical thing to play around with, right? You can now do percolation on it and do all sorts of fun little games. Because it's got an exponential growth as you go out from, let's say, this root, then it's going to fill space absurdly, right? So this thing fits in, if you want to embed it somewhere, ultimately in some sort of arbitrarily high dimensional space. So in terms of being a model for actual networks on surfaces, is not great, but people had a lot of fun with this. There's sort of a stat mech thing you can do, which is count up all the lattice animals, right? That's actually one of the better terms in stat mech, right? Lattice animals. So you just make every little possible, you start here and make every little possible subgraph, and then you count up how much area they take up, right? Which is just going to be the number of nodes, and then longest stream length, and you do those sorts of things, and you can get Horton's laws and all these sorts of pieces, right? So it turns out, yes, they satisfy Horton's laws and Tokunaga. Well, that's an interesting one. I'm not sure about that because no one was thinking about Horton's laws at the time. So as I said, they're not connected with surfaces. Not good at all. But this was a paper. Who's this by again? One of these papers that comes along, Kirchner, who basically says you're all idiots. You know, like it has that feel to it. Like, what are you doing? Every branching network just does this. There's nothing interesting here, right? We're going to return. Speaking of, more recent version of that, we're going to come back to the little interaction between our friends online about power laws, which is fun. So more people said things. Okay, so I talked about Scheidegger's model, which was this very nice thing. So of course, this is sitting in 2 dimensions. There's no problem with that. It's a triangular lattice, flipping coins for left and right. And this proves, so because of random networks, and we understand those things, we have lots of good stuff there. And I won't show it here, but basically it does satisfy Horton's laws and Tokunaga's laws, but they have funny numbers, right? They don't have numbers that are, they have interesting, complicated numbers that no one's derived analytically. That's fine, doesn't matter. But for the power laws, for drainage area and basin length and so on, they come out of river networks, as we talked about. They come out of random walks, I should say, as we talked about, and they have specific exponents, right? So Hack's exponent, for example, which is the way the mainstream length scales as area, is to the power of 2/3. All right. So it's a universality class, right? So that's a kind of a whole world of branching networks would fit into that box. There's a much more complicated thing came along, at least in trying to involve physics and so on. The actual simulation perhaps not as complicated, but so now we have landscapes, and we're going to think of them again as these sort of satellite ones, right? So they're on a grid in terms of the evolution of, in terms of the simulation. And so the idea is that landscapes evolve such that it's an optimization story, and this is something we're really drawn to. It's true in a lot of areas of physics. Although we're sitting here with brains, which aren't really the most optimal objects in some ways. They're pretty good in terms of wattage, but a lot of the thinky bits do silly things. And platypuses. All right, but anyway, optimality is definitely a huge part of the real world. So the idea is there's going to be some flux of material, some force. We'll talk about this a little bit later for some other optimality things. And then the idea is the flux is going to be how much water is flowing through. Well, that's going to be proportional to the drainage basin area, right? So this is a non-local measure. So you have some point, of course, and you have the drainage basin area, and that's going to then represent the flux. This could be some power, but it's not. This is the slope, the local slope. So steeper, the more forceful, right? So you've got some amount of fluid coming through, and the steeper it is, the more impact it has on the landscape. And then this was used for that piracy stuff as well, right? This is an old story in geomorphology that slope scales very, very roughly as area to some parameter. So they just said, okay, we'll just make it some exponent, and we'll play around with that. You get landscapes that produce things that are somewhat near real networks. The numerical method matters, which is a problem. That's a bit disconcerting. And then a few years later, after all this came out, some of the Maritain, who's part of this team, we'll come back to, we'll see Maritain again. When we come to blood networks, showed that actually these systems produce 3 universality classes. The Scheidegger ones, which are fine objects, but you don't really see them in the real world. Self-similar ones, which are kind of not interesting because all the basins are self-similar. There's no crazy allometric scaling. And then a third kind of random network, which is a random resistor network. So that's okay, but there are so 3 universality classes, not as general. And this is just some little summary of that. You know, this is the game we kind of talked about, which collapsing all these scaling laws for these networks, right? There was this whole list of them, and we got to this idea that really only a couple of parameters mattered. So this was Hack's exponent, which is how length scales with area in a basin, and D is the fractal. Here it is. It's the fractal scaling for the mainstream length in a basin. Very weak usually. So there are these kind of classes, right? So real rivers have this kind of, they're a half going up. We'll come back to this because this is this sort of big story for real, for large landscapes. And these are these optimal channel networks from Rodriguez Iturbi and Ronaldo. Ronaldo, lovely guy, played rugby for Italy actually for a while, which isn't saying that much, I suppose, but yeah, good for him. Big strong lad. I mean, it's not New Zealand, right? Okay. So that's all I think about. Let's see. So so this is Scheidegger directed random networks 2/3 for the Hack exponent. So you see, you get some interesting things, right? And you might start to say, okay, well maybe our landscape on Mars or on the side of a volcano is one of these, possibly. But as I said, no one's really. There isn't something I think for landscapes that's really universally agreed upon in terms of mechanism. Obviously we know how erosion works, but it is a complicated, messy business. Trying to sort of, think about the very small scale and zoom that up. Anyway, so this is just a quick summary, and then we'll wrap up this piece. So we have these structural laws of Horton and Tokunaga. We showed that they fit together, and that was a big step, right? Describe until you're pretty happy about that. Okay, let's explode this thing. Correctly done. So these are, right, we're not worrying about slopes. Lots of scaling relationships. Got all these parameters, right? The Horton ratios for numbers and lengths, and there was also area and stream segment lengths, and we saw that those things collapsed. Oh, that's my little problem. I miss these sometimes. This is using Z-LaTeX has made a mess of these. They should be natural logs. Oops. Okay. This is what you want to do for these big systems. If you can show there are only a couple of scaling exponents that matter, then you've achieved something. And of course, that's describing, and we've got to get to mechanism. Okay. This should be ln of R L over ln of R n. Right. Oops. We can do the distribution thing. I kind of jumped over that. And then lots of models, but nothing that's complete. I mean, we'll see. Okay. That's what I wanted to show you. It was just a very quick little piece about mechanisms, which in some ways shows you how far we have to go.